say a few words about the safety assessment of nuclear reactor aging. As you kindly said, I work in IRSN. IRSN is one of the stakeholders for nuclear safety in France, among others like operators, public authorities, and stakeholders, including civil society organizations such as NTW. IRSN is a French technical safety organization. We are independent from operators. We possess a detailed knowledge of installations, and we also have a role of safety watchtower because we monitor operational experience feedback, and every year we publish a report on the state of the fleet of nuclear MPPs in France, and in this report we address such topics as nuclear aging. And also we are a research institute, and our research topics include nuclear aging. So, like it has been said before, most NPPs have been designed with a given lifetime in mind. Depending upon the countries, it is or not a regulatory limit. And in France, there are no regulatory limits, but the design lifetime was 40 years. But for economical reasons, most operators want to operate NPPs beyond this time span. But meanwhile, knowledge has increased in 40 years. We have new experience feedback, new research and development results, and there are new opportunities for safety improvement. On the other hand, we have new designs with more stringent safety objectives, like the so-called third generation nuclear power plants. And so we have to deal with the coexistence of old and new reactors. So the main question here is, under what safety conditions can a prolonged reactor operation be accepted, taking into account the fact that safer technology is available? The first thing you have to do when you want to go beyond this initial lifespan is to demonstrate that you are able to manage time-dependent effects. And the second point is you have to reduce the safety gaps between old and new plants in order to make LTO acceptable. So we are going now to review these two important aspects. Managing time-dependent effects. Of course, you have aging management itself. The presentation shows samples of the effects of aging on nuclear power plants, and I will say a few words afterwards, but it's not limited to that. So I've listed here other important topics. First one, the ability to prevent, anticipate, and cope with discrepancies. Some of these discrepancies come from aging, other from maintenance errors, and some were there from the beginning, but we just have discovered them. So it's very important that the operators are able to prevent, anticipate these discrepancies, and to bring the solutions in a quick and efficient way. Also, there are the subject of plant modifications. The operators, during the lifespan, wants to put changes to its installation, and sometimes the safety authorities ask him to do so. So the reactor is changing, and you have to check that the safety demonstration is still valid. There are other topics like obsolescence management. Obsolescence means that the manufacturer that constructed the equipment important for safety does not exist anymore or has stopped the line of product. So when the component gets older, you have to replace it with new technology. New technology means a new safety demonstration. There is also the subject of human resources and knowledge management, but I will not develop this point because it's the next presentation. And even if nothing changed at the plant itself, you have to take into account the modifications of its environment, new industries near the plant, or environmental changes. And these changes can bring new threats that the operators need to be able to face. Reducing the safety gap between old and new plants. Of course, to do that, you must use operating experience feedback. And there is in Europe a very useful tool to do that, which is called periodic safety reviews. And one of the objectives for us is to enhance prevention of accidents, but also to reduce the radiological consequences of accidents if they do happen. You can do that by enlarging the scope of the probabilistic safety assessment studies, including topics such as flooding, earthquakes, and so on. And there is also a very important objective, which is to improve operation conditions of the plant. So now I will zoom in the topics which were underlined in those slides. First topic, aging management. The main objective here is to maintain availability and effectiveness of all SSCs. SSC stands for structure, system, and component, important for safety. And we have to make a distinction between replaceable SSCs, like electrical cables, valves, and non-replaceable SSCs, like the reactor pressure vessel or the containment building. The key issues here are the knowledge of degradation mechanisms. The operators have to use their experience feedback, research developments in order to increase their knowledge of degradation mechanisms. And then they have to perform an evaluation of the effectiveness of maintenance to detect these mechanisms. If necessary, they also have to enhance their maintenance effectiveness as the plant grows older. There is also an important issue, which is plant monitoring, especially when degradation mechanisms are not well known. You have to check periodically components in order to see if they are still working well. And of course, the aim here is to repair or replace the component before safety issues occur. As an example of that is the extension of qualification durability. Qualification is the demonstration of the ability of SSCs to work in extreme conditions resulting from accidents, pressure, temperature, dampness, and so on. And usually, when the plants were constructed, these demonstrations made assumptions about the lifetime of the component itself. If the lifetime is extended, so shall be the demonstration. So, operators may have to perform new tests in order to check the ability of the component to keep its qualification for a longer time span. About reducing the gap between old and new plants, I will say a few words about periodic safety reviews. Their objectives are the following: to assess the cumulative effects of plant aging and plant modifications, operating experience, technical developments, and siting aspects. And we do that every 10 years. And this includes an assessment of plant design and operation against current safety standards and practices. And the objective is to ensure high-level safety throughout the plant's operating lifetime. So of course, by nature, they are the most efficient way we have to reduce the gap between old and new plants, because the safety objectives you use for PSRs are the new ones. And last topic, enhancing prevention of accidents. Here, the objective is different when you deal with design basis accidents and severe accidents. With design basis accidents, the objective is to enlarge the scope of the accidents and the robustness of the assessment. I will give a few examples. And for severe accidents, the idea is to search for high-impact solutions able to prevent severe accidents, core melt, and mitigate consequences more efficiently. For design basis accidents, the key issues are adding new possible accident scenarios to the safety analysis report. For example, accidents specific to shutdown states, which were not taken into account at the beginning of the plant, and they have been added to the safety case. Another example, lengthening the time limit for operator actions. There is an assumption in the safety report that even if operators, in case of an accident, do nothing during 20 minutes, they will still be able to put the plant back into a safe state. This time limit is being extended to 30 minutes, so there is an increase in the defense in depth. For severe accidents, one of the tools that the operators can use is using probabilistic safety assessments to identify ways of improvement and to check their effectiveness. The ways of improvement depend on the state of the design. For example, in France, EDF has been has improved the reliability of electrical sources, and intends to increase water storage for safety functions in order to have a longer grace period in case of an accident. Of course, Fukushima arrived, and most intended post-Fukushima improvements will increase the ability to prevent severe accidents and to deal with them if they would happen. Just for a conclusion, I would say that these measures have a cost, but they do cost far less than the accident itself if it happens. So it is a very important issue to put some effort and money into these topics.